Hello, welcome to my channel. In this video, I'll be discussing simple harmonic motion. Simple harmonic motion describes motion of object that oscillates back and forth in a regular pattern and is a type of periodic motion. What does this mean? Let's say a string tied to a body is tied to the roof and the body is made to be suspended. If this body is displaced to a position like this and it is released, what we witness is that the body will tend to move back to its equilibrium position. And when it reaches this equilibrium position, it overshoots the place and return back to the other side, extreme end of the other side. When it reaches this place and the velocity reaches zero, it return back and continue to move like that. This to and fro motion is what is known as simple harmonic motion. Let's take example of let's take another example of a string that is attached to the wall and is tied to a mass. If this mass is displaced, if this string is pulled with a force F to this position and is released, what we witness is that this string bounces back and tends to return back to its original position. And when it reaches this place, it overshoots its position and it will continue to move in this direction until it reaches a position here. And following this, it moves back again and overshoot this position, this is equilibrium position, to reach this place again, and it continues like that. If there is no external force acting on this body, it continues to oscillate till eternity. And here also, if there is no resistance, external resistance like force, like here resistance, it will continue to move like that. Okay. The driving force in this kind of motion is what we call the restoring force. And the restoring force is directly proportional to the displacement and acts in the direction opposite to that of the displacement. If this body is displaced here, the restoring force tends to keep it back to its equilibrium position. And when it is released, it is that equilibrium force that forces it back. Sorry, it is that restoring force that forces it back to go back to its neutral position. And the restoring force is usually equal but opposite to the displacing force. Okay, like in the case of this mass spring, when the body is pulled such that the string is extended to this place, the restoring force will be the backward force that will tend to keep it back to its equilibrium position. And it is this force that drove it back to this position when the body is released. But because the body, when it reaches this position, is already moving at a velocity v, it tends to overshoot this equilibrium position such that it's moved to the opposite direction and reach the extreme here, compressing the string to its new amplitude position here. Okay, so this is what simple harmonic motion is, and this is what drives it. In simple harmonic motion, there are terms that are very important to understand. And one of these terms is what is called the period. The period is the time taken for the body to complete one oscillation. And one oscillation is described as oscillation that moves to this place and back. So the time taken for the body to move from one extreme to other extreme and back to its starting position is what is called period. And it is given by this formula 2 pi over angular velocity. What does this mean? We know that angular velocity is equals to the cycle, complete cycle in oscillatory motion is given by 2 pi, which is derived usually from a circular body in circular motion. When a body completes a circular path in a circular motion, it already moved 2 pi because pi rad is known to be 180 degree. So 2 pi is 360. So this is where this 2 pi comes from. And the time taken for the body to complete one cycle like this is the period t. So as we know that the angular velocity is the angle traveled over time taken, and we know the time taken for the body to travel a circular path is period t. So this gives us this equation, and when you make t subject of the formula, t equals to 2 pi over angular velocity. This is where this formula comes from. Okay. The next term we'll be talking about is the frequency. The frequency is the number of cycle completed per seconds, and it is given as f is equals to 1 over t. And since we know that t is 2 pi over w, this can be equals to f equals to 1 over 2 pi over w. And when you somersault this, it becomes w over 2 pi. Okay. Amplitude refers to maximum displacement from the equilibrium position. For this body now, for a body that is suspended like this, the example of a string I gave the other time, let's say this is the equilibrium position. When the body moves, the maximum distance, the maximum displacement from this its equilibrium position is what is known as the amplitude. Displacement for an oscillating body, the displacement is given as function of t equals to a cos angular velocity times time plus psi. Okay, this is the displacement. In physics, velocity expressed as a function of time is usually the first differential derivative of the displacement, and this is given as when you differentiate this the x dt, it will give you minus a w sine wt, which is angular velocity times time, plus psi, which is a phase constant. And this equation expresses the velocity, the linear velocity of a body undergoing simple harmonic motion. To get the acceleration of a body undergoing simple harmonic motion, the differential calculus of the velocity, linear velocity expressed as a function of time, will give us the acceleration, and the acceleration expressed as a function of time will be minus a angular velocity squared cos wt plus psi. Okay, so this express the linear acceleration of a body undergoing simple harmonic motion. Now, we've known the displacement, velocity, and the acceleration. How does this vary in a body undergoing simple harmonic motion at different points in time? Let's take, for example, a body is hanged. Let me take the example of a string tied to a body, as we have been doing. Usually, when the body is displaced to this point A, let's say someone held it and displaced it up to this point. At this particular point, the displacement is maximum, okay? And that will happen to be the amplitude of the body, okay? The displacement is maximum at this particular point in time. When the body is released, the body accelerates, and the maximum acceleration is usually seen at the initial release of the body. The acceleration is maximum at this particular point in time. And when the body move, the body at this point in time, the body has Vmax, that's where the maximum velocity usually occur. And the acceleration at this particular point in time is zero. So this body, when it's continue overshoot its equilibrium position, it move to this point B. Similar to this place, this is the amplitude. That's the maximum displacement on the, if this happen to be the positive direction, this will happen to be in the negative direction. And at this particular point in time, the velocity is equals to zero. The velocity is zero at this particular point in time. The displacement is maximum, and that's the amplitude, and the acceleration is also maximum at this particular point in time when the body start to move. So this is how the displacement, velocity, and acceleration varies across the different phase of a body undergoing simple harmonic motion. Usually, a body undergoing simple harmonic motion obey the principle of conservation of energy. The mechanical energy, the mechanical energy of the body is equals to kinetic energy plus the potential energy. Usually, the potential energy of a body, let's say this is a string, and this string is pulled by a force F. At this particular point in time, the potential energy at this particular point in time, this string, if it obey Hooke's law, we know that this force will be equals to kx, where force is the force applied, k is the modulus of the string, and x is the displacement. And x is the displacement. The resolving force usually acts in opposite direction, and is usually equals to this force, but it is in opposite to this force. Okay, so for us to get the potential energy of this string at this particular point in time, we need to get the integration. When you integrate the force, it will give you, when you integrate this force, it will give you 1 over 2 kx squared. This happens to be the potential energy of this string at this particular point in time when it is held here. It will be 1 over 2 kx squared. Take note of this equation so that if you are asked the potential energy of a string that is stretched to a distance x, you'll be able to calculate it. You don't need to know the integral calculus before you get this. Just take note that this formula come from integral calculus. of the force. Okay, and this happens to be the potential energy. Now, when the body is released, it moves with, like I said, that it moves with a velocity towards this direction, and the velocity increases until when it is maximum here. Okay, meaning that given that the kinetic energy is equals to 1 over 2 mv squared, since this v, the velocity will be maximum at this particular point in time when the body reach its equilibrium position, and we know that mass is constant, meaning that the kinetic energy at the equilibrium position will be maximum for a body undergoing simple harmonic motion. The kinetic energy will be maximum at the equilibrium position. So take note, the potential energy is maximum at the maximum displacement, and that is due to the fact that the x is maximum at points of maximum displacement, which is the amplitude. So the potential energy is maximum at the extreme position, and the kinetic energy is maximum at the equilibrium position. So at the extreme position, the potential energy is maximum. But observing the principle of conservation of energy, at any particular point in time, the mechanical energy of the string or the body undergoing simple harmonic motion will be equals to the sum of the kinetic energy and the potential energy, meaning that mechanical energy will be equals to the kinetic energy, which is 1 over 2 mv squared, plus the potential energy 1 over 2 kx squared at every point in time. Okay, and we know from the previous slide that the velocity, the linear velocity, is minus aw sine this. So when we substitute it in this equation, we are going to get me will be equals to 1 over 2 m brackets minus a sine wt plus psi, right? Everything squared, okay, plus 1 over 2. And we know that the displacement from the previous slide is a cos this. We know that the displacement is a cos angular velocity plus psi squared, right? Remember to put the angular velocity here because that's what v is. This is how energy changes in simple harmonic motion. The mechanical energy at every point in time remain constant, meaning that at every stage of the motion, no matter where it is, when the kinetic energy is added to the potential energy, it always gives you a particular value which is constant. And that particular value that is constant is equals to the initial potential energy when the body is first released, and that is taken to be half ka squared, in which a happen to be the amplitude before it is released to go into the oscillatory motion. Take note of this. the principle of conservation of energy, the sum of the kinetic energy and potential energy is always equals to a constant value of mechanical energy. And that constant value is equals to the potential energy of the body before it is released to start oscillatory motion. Before we go, there's another concept I want to talk about. Recall that I said earlier that when a spring is stretched to this extension, okay, the restoring force is usually equal in magnitude to the force that is stretching it, but it's usually opposite in direction. Okay. And since we know from the Hooke's law that the force is equals to K times the extension, okay, meaning that will be equals to the restoring force will be equals to minus kx, okay, which is equal in magnitude to the force that is displacing it, but is opposite in direction, which is signified by the minus value. Okay, and also recall that in Newton's second law of motion, force is equals to mass times acceleration. Okay, so if we say mass times acceleration is equals to minus kx. And don't forget that we said earlier in the slide that acceleration, when expressed as function of t, is equals to what? Minus amplitude omega squared cos omega t plus psi. Okay, this happens to be the acceleration. And the displacements, we express it as x when expressed as function of t is equals to a cos omega t plus psi. Okay, when we substitute this, both of these in this equation, what we'll get is mass bracket minus a omega squared, or let's say you can also call it omega squared a cos omega t plus psi, right? Which will be equals to this minus k which will be equals to minus k times displacement a cos omega t plus psi. Okay, now if you look at this, if you can't see it well, this is what I brought here. Okay, take note of that. So if you look at this, on this side we have a cos omega t plus psi on this side, all right, and we also have it on this side, right? A cos omega t psi. You can see that we can, if we divide both sides by this value, it will cancel out, right? So what we have left is m, what we have left is m omega squared is equals to minus k. which is equals to minus m omega squared is equals to k is equals to minus k. This minus cancel minus. So what we have is m omega squared is equals to k. This shows the relationship between the spring constant and the angular velocity. Okay, so you may need this equation at some point. Forced vibration is a situation whereby a body undergoing simple harmonic motion made another body to undergo simple harmonic motion. What do I mean? You can conduct an experiment in which a rope is tied between two walls and hang gets a string tied to maybe a stone or a different body. Get different of them tied to the rope like this. When this body is displaced and is made to undergo oscillatory motion, you observe that without touching this other body, this string can make the remaining body to vibrate. Okay, when it can make the remaining body to oscillate. When it happens like that, that is what is called forced vibration. When a body is made to vibrate, for example, if this one is displaced, it will be undergoing oscillatory motion at its natural frequency. But when it is displaced like that and is released, when it's make this other body to oscillate, these other bodies too can be oscillating in their natural frequency, or they may be made to oscillate in a frequency that is different from their own. And this can be observed when tuning fork is used to make a body to vibrate. Okay, this can be gotten if you tried it in an experiment, which we may not be able to do in this video. If you want me to do a video that will explain this experiment, you can comment in the section below. So when this body is displaced and is made to move, it can also make this one to move at its frequency. And if you look at the length of this rope, their frequency will be the same. Okay, so meaning that this body can make this body to oscillate at its frequency, at its natural frequency, because their frequency is usually the same. When it happens like that, when a body made other body to vibrate at their natural frequency, that is what is called resonance. Okay, this may sound technical, but if you want me to make video on this, you can comment in the if you want me to make more extensive video on this, you can comment in the section below. And take note of this because you may be asked. Having gone through the explanation of simple harmonic motion, the displacements, velocity, the acceleration of the body undergoing simple harmonic motion, and also the changes in energy, let's go through some questions to test our understanding and also reinforce what we have known. Question number one, it says the restoring force in simple harmonic motion is dash A constant, B directly proportional to the displacement, C inversely proportional to displacement, and D independent of the displacement. Recall that when I was giving example of a string that is displaced, I said that when a body is displaced with a force F, there is usually a restoring force that acts in opposite direction and it's equals to the force that is displacing it, but it is usually in opposite direction. So remember that in from Hooke's law, force is directly proportional to the extension, and this is force equals to Ke, where K is the modulus constant. This E is the displacement, okay? And we say that the restoring force is opposite to the displacing force, but it is equal to it. So As the force increases, the displacement increases, so they are directly proportional. Okay. The next question, the displacement in simple harmonic motion is given by, you can see this in the earlier slides view that I talked about, which is A cos theta. Which of the following is not an example of a system exhibiting simple harmonic motion? Mass string, this is correct. Simple pendulum for a small angles, this is correct. Damped pendulum. Damped pendulum, let's say a body is hung like this and it is displaced. It is said to be damped when there is an external force opposing this resolving force. And this external force can be in the form of air resistance. So that's damped pendulum. And one of the assumptions in simple harmonic motion is that there is usually no external force acting on the body undergoing simple harmonic motion, such that their amplitude is preserved and they continue that motion until eternity. However, in reality, when you hang a string like this, when you displace it and you leave it to oscillate, at a particular point, it will come back to its equilibrium position, and that is due to the air resistance around. So, in reality, it may be getting a perfect simple harmonic motion may require some extra effort to remove this air resistance. Oscillating molecules, this is correct. So, the answer, the body that is not an example of simple harmonic motion is this, because there is usually a damped effect by the external forces. The time period in simple harmonic motion refers to, I believe you should be able to do this. The relationship between period and frequency, I think you should be able to do this. Comment in the section below what your answer is, and I will respond to you. If you want me to make videos on, especially on a particular part of this lecture, you can just comment in the section below and I will respond to that. In equilibrium position, simple harmonic, the kinetic energy is, I should believe you should be able to answer this correctly, because like I said, the velocity is maximum here. And when velocity is maximum, that will increase the kinetic energy to its maximum. Okay. The amplitude of simple harmonic motion is, this is earlier said. You can pause the video and answer in the comment section below. Okay. The angular frequency is related to the time period t by, angular velocity is 2 pi over t. Okay, I believe you should be able to get this in this. So comment your answer in the section below. So recall that frequency is equals to 1 over t, and this is the same thing as 2 pi times 1 over t, which is the same thing as 2 pi f. Okay, so is equals to angular velocity. So the frequency will be what? Angular velocity over 2 pi. Okay, so you can get your answer here. Okay, sorry, there is a typo here. This is angular velocity. Okay, I'll leave the remaining questions for you to answer. Go through them, write your answer in the comment section below, and let's open up discussion. If you're not clear about anything, you can comment in the section below and I will explain more extensively. Don't forget to like, subscribe, and share. The energy that keeps me going is you liking this video. Share it with your friends to benefit and subscribe. And after subscribing, don't forget to hit the bell icon for you to be notified when I make new videos. Okay? Thank you very much for listening. Till I see you in my next video. Take care and bye bye.